In this video, we're going to be covering data serialization or data compression by using the buffer library, which is a super neat library that grants you low-level access to read and write from memory blocks known as buffers. And this allows us to compact data when we need to send it through remote events, or compact data that needs to get stored in things like memory stores or data stores. The primary use for buffers are going to be for when you need to work with a lot of binary data, maybe making your own custom replication system and compressing data through remote events, if your game needs it. Otherwise, you probably won't likely benefit much from buffers in your projects, unless you want to mess around with them for fun. And a great way to check to see if buffers could be something that you would use for your game, maybe for your game networking, is by observing your game's network statistics and see if something like your receiving data exceeds, 50 kilobytes per second is a pretty good standard that people set. So if you go to, for example, in Studio here, there's a network tab. I'm pretty sure you can open this up when you're in the Roblox client using, I believe it might be Shift F2 or Shift F3, something like that. You're going to see in here incoming and outgoing data. If your incoming data exceeds overall like 50 kilobytes per second, and that's something that consistently happens in your game, then maybe you might want to take a look at seeing if you can use buffers to reduce overall incoming or even overall outgoing data, just to make it better for anyone who has slower internet access. We're also going to be taking a look at loleris's Sera Module, which is designed to make it really easy to work with buffers and send serialized data through remote events and then deserialize it on the receiving end. So, speaking of buffers, let's buffer to the next portion of this video to talk about today's sponsor, Brilliant! Brilliant is an online learning platform dedicated to help you get smarter every day. They have thousands of interactive lessons in math, science, programming, data analysis, and even AI. Each lesson is filled with hands-on problem solving that helps you experiment and play with concepts, which is a learning route proven to be much more effective than simply watching lecture videos, like this one. Brilliant offers a great mix of competitive features, daily encouragement, and engaging problems to keep you motivated and on track for learning new skills. And you'll have no excuses either, because Brilliant's mobile app makes it really easy to learn from literally anywhere, right from your phone. So even if you're sitting on the toilet, doom scrolling, you can instead spend 5 minutes of your time to learn with Brilliant and sharpen your skills. Many game developers express the frustration of lacking crucial math skills needed for making complex and fun systems in their games. And Brilliant has got you covered. With many lessons in various mathematical concepts such as linear algebra and even calculus, you can take those newly learned skills and apply them directly into your programming projects. If that sounds awesome to you, it's going to be even awesomer because Brilliant is offering 30 days for you to try out their learning platform absolutely free. Head over to brilliant.org/crusherfire or scan the QR code on screen. You also get 20% off an annual premium subscription. Thanks to Brilliant for sponsoring this video. So, to know what the heck a buffer actually is, we need to refer to the documentation, because obviously the people that wrote the buffer library are going to be the ones who know it the best. A buffer is an object that represents a fixed size, mutable block of memory. The buffer library provides functions for creation and manipulation of buffer objects, providing all its functions inside the global buffer variable. Buffer is intended to be used as a low-level binary data storage structure, replacing the uses of string.pack and string.unpack. Use cases include reading and writing existing binary formats, working with data in a more compact form, serialization to custom binary formats, and the general work with native memory types like fixed length integers and floats. When passed through Roblox APIs, including sending a buffer through custom events, the identity of the buffer object is not preserved and the target will receive a copy. Similar to other limitations, the same buffer object cannot be used for multiple actor scripts if you're using parallel luau. Many of the functions accept an offset in bytes from the start of the buffer. Offset of 0 from the start of the buffer memory block accesses the first byte. All offsets, counts, and sizes should be non-negative integer numbers. If the bytes that are accessed by any read or write operation are outside the buffer memory, an error is thrown. So, gave us a pretty good description of what it is. A fixed size, mutable block of memory, and we can create a buffer through the create function. Creates a buffer of the requested size with all bytes initialized to 0. So we pass it a size here, and this size represents the size of the buffer in bytes. And 1 byte represents 8 bits. So we can create a buffer up to 1 GB. But I doubt you'll ever need a buffer of that size. Now, to read and write from the buffer, there's a whole bunch of read functions and there's a whole bunch of write functions. So you have your read for integers and unsigned integer, as well as floats, and the same thing for writing to it. These names are going to look a little weird, but they're pretty intuitive. So for example, with this function here, read I8, you're probably thinking like, what the heck does this mean? I stands for integer. 8 represents how big this integer is in bits. So this is reading from a buffer an 8-bit integer, or a integer that has a size of 1 byte, because remember, 8 bits, 1 byte. So this is reading 8-bit integers. You also have one here called read U8. Might be thinking, what the heck's U8? Well, U stands for unsigned integer. And you're going to be thinking, wait, what the heck? What's the difference between integer and unsigned integer? Well, this includes any integers that might also be negative. So this will give you a range from, I believe, a negative 128 to 127. That's the size of numbers that can be represented by an 8-bit signed integer. If you have an unsigned integer, well, that range goes from 0 to 255 because it doesn't include any negative numbers because those have the negative sign, right? So we throw out the sign. If you don't need negative numbers, then we can use unsigned integers. And that is literally all of these functions. This is a 16-bit integer. This is a 16-bit unsigned integer. This is a 32-bit integer. This is an unsigned 32-bit integer. And then this is a 32-bit float. And then this is a 64-bit float, or sometimes in other programming languages, they would call this a double because it has higher precision than a 32-bit float. I believe a 32-bit float can have up to like 7 decimal points. What was also recently added to the buffer library were the read bits and write bit functions, wherever it is there. Read bits and write bits. So usually with all of these functions, you are reading bytes. But if you want to read individual bits and write individual bits, then you have the read bits and the write bits functions. Read bits, write bits. And here in the documentation, the read bits is equivalent if you pass the arguments, for example, here. Let's say you have a buffer, you want to start at 0 or byte 0, and you want to read 8 bits. Well, 8 bits is 1 byte, so that's the same as reading an unsigned 8-bit integer. Or for example, with this one, you want to read 0 to 16 bits. Well, that's going to be the same as reading an 16-bit unsigned integer, and so on and so forth. And this also allows you to read and write 24-bit integers or 24-bit numbers, because by default, there are no 24-bit read or write functions in here. The write bits function says it will write data to the buffer based on a specific bit count integer from 0 to 32 inclusive. Value is treated as an unsigned 32-bit integer, and only the amount of bit count least significant bits are written, and this has to be also within a range of 0 to 32. Note that a 0-bit width is supported only to not error in generalized cases where bit count is dynamic, and writing 0 bits has no effect. So with these new additions of the read bits and write bit functions, because these weren't here before, these are actually my first time seeing them here, they must have added them like, I don't know, a week ago or something. Now you can compact data even more inside of a buffer. Because by default, when you create a buffer, you can create it in byte sizes. You can't make like a 1-bit buffer. It has to be a byte. But that means if you make a 1-byte buffer, that's 8 bits of storage. If you have a number that you know is only going to be, let's say, between the value of, I don't know, 0 and 10, there's really no reason to be storing it within an 8-bit integer. You could compact it down and only write the bits, and you could store multiple numbers within a single byte in a buffer. So, yay, even more data compression. There's also some other cool functions in here, like you can copy bytes from a buffer to another buffer, and you can also fill a buffer starting at specified offset to value. And there's also some for reading and writing strings. This is specifically when you create a buffer from a string and this string has like some buffer data in it. I believe this relates to another library. You probably won't use these functions. The main ones you're going to be working with are going to be reading and writing floats and integers to your buffer. And you can also check the length of the buffer by calling the len function, which returns what the size of the buffer is in bytes. But seriously, that's enough reading documentation. We actually need to look at it in a game. So let's write some code. Let's make a buffer. I'm going to call it B, and we're going to do buffer dot, and we're going to create a new buffer. And this buffer is going to have a size of 1 byte. So we're reserving a block of memory in the computer's memory that contains 1 byte of storage. And now we have this buffer, we can use the other functions within the buffer library, like read and write, to read and write values to our buffer. So for example, let's say I want to write an 8-bit integer to the buffer. Now you might be wondering, how do we know what the range is for these different bit size integers? Well, let's do some math here real quick. We know that a bit can be either 0 or 1. You got two possibilities here. And let's say you have 8 of those bits in a byte. So if we do 2 to the power of 8, and then since numbers start counting at 0 and not 1, we're going to subtract 1. If we print this, if we have an 8-bit integer that's unsigned, so if we were to do an 8-bit unsigned integer, the range would be 0 to 255. And you might notice that's the same values. If you were to do something like color3 from RGB and you pick like a color value in here, you can see how the range of these values go from 0 to 255. And that's also where you get the saying like 8-bit color, because you get to pick 8 bits for the red, green, and blue values for a color. So for example, white is 255, 255, 255. Each of these numbers are 8 bits. This is an 8-bit integer, this is an 8-bit integer, this is an 8-bit integer. These are unsigned integers because you can't have negative colors. That doesn't really work. So if you're going to have an 8-bit integer, that's 0 to 255. Now if you wanted to include negative numbers, so that would be a signed integer, then what we need to do is we need to divide this by 2, because we need to represent values in either direction. So the lower limit would be negative 128, and the upper limit would be 127, because you need to subtract this by 1 since counting starts at 0. So an 8-bit signed integer represents a range from negative 128 to positive 127. And then we can just continue doing math here. So if you wanted to represent a 16-bit unsigned integer, 2 to the power 16 subtracted by 1, that means we can represent any number from 0 to 65,535. And again, we would divide that by 2. So if we divide this by 2, the upper range would be 32,767. Remember, we got to subtract 1. And the lower range would be negative 32,768. That would be for a signed integer. And again, we can keep going up higher. If we wanted to represent a 32-bit number or integer, that is the upper range. What number is that? 442. There's no commas, so it's kind of hard to read. Let's see. We got 100, 100,000, 290. So this is like 4.3 billion, whatever. That's how many numbers you can represent. And then of course we can go all the way up to 64 bits. And yeah, so that's all the numbers you can store inside of there. And then with floats, the precision will determine how many decimal points there are for your float. So by default, it gives us 32-bit floats and 64-bit floats, or doubles. Now you can also reduce this down. So for example, let's say you had a number, and you know this number was going to be between 0 and 1, some kind of value between 0 and 1, and you don't need it to be super duper precise. Like let's say you had a decimal like 0.39151 5, whatever. Let's just say you had a number like that and you don't really care about precision too much, but you generally want to keep this decimal point. You could actually store this within 8-bit signed or unsigned integer by just converting it into what this value would be represented between 0 and 255. Like what is 39% or 39.1% of 255? You can represent that as an integer, write it into a buffer, deserialize it, divide it by 255 to get a rough estimate of what the original value was. So that way you don't have to write to a buffer with a 32-bit or 64-bit float if you don't need that much precision. Okay, enough of me talking. Let's write a value to this buffer. So here's our buffer. We're gonna write an unsigned integer to the buffer, starting at the offset. Ooh, I'm using read. I need to write. Write an unsigned 8-bit integer into the buffer. We're going to start at the offset of 0. So we're starting at byte number 0, and we're going to write 150 to the buffer. And then afterwards, we can actually read this value using the read, because the buffer library needs to know what the heck value it's reading. In this case, we want to read an 8-bit unsigned integer inside the buffer. And where is this 8-bit unsigned integer stored? Well, it's stored at offset 0. So the first byte inside of this buffer is going to be taken up by this 8-bit unsigned integer. So we could print this here. We could run the game. Actually, let's see if load string's working. I wonder if they fixed that. Load string enabled. Let's do load string game.server script service script dot source. Did they fix this? No, they didn't. Oh wait, There's something wrong with my code. Did they fix it? Hey, they fixed it. Wow, I reported that as a bug and they actually fixed it. Roblox. Dang. Okay, cool. I don't need to run the game. I could just do this. So we get 150 from our buffer. There we go. We stored it inside of a single 1 byte buffer. We wrote our 8-bit unsigned integer and we read our 8-bit unsigned integer. And the cool thing about this is by default, when you send a number through something like a remote event, that's going to use 9 bytes. Because by default, it's going to assume that this number is 64 bits, and it's not going to do any like compacting of data for you. It's just going to send a 9-byte number. And to prove that, let's make a remote event. Let's throw a remote event in here. My event. Let's get a local script. Let's get replicated storage in here. My event, replicated storage. My event. Set that equal to that. And then my event on client event value. We'll just print the value out, because basically what we're going to do is we're going to use this packet profiler plugin to see the size of packets coming in. And then in here, you just have a while true do loop. Replicate storage. Let's get my event, replicate storage, my event, fire all clients. Let's pass in, we're actually going to pass in 2 values. We're going to pass a table. We're going to call this not serialized, which is 150. And we're going to call this serialized, and that's going to be equal to our buffer. And we'll just do this every single second. Okay, let's play test the game now. Playing the game, and then let's go to plugins. We're going to open up the packet profiler. We're going to open up this chart. Let me increase the size of this chart so we can see it. And then I'm just going to pause it. Here's our packet, and let's take a look at our packet. The total size of the packet was 55 bytes. Most of those bytes came from the strings, because each character of a string is 1 byte size. But look at that. Here is 150. That took 9 bytes. It's assuming that this is a 64-bit number, and we took 9 bytes. There is a little bit of overhead. Same thing with the buffer thing here too, because you would think, hey, isn't this supposed to be like 1 byte? But since the buffer is also storing information like it's a length and stuff like that, there's going to be a couple extra bytes for some other stuff. There's a little bit of overhead, but you can see that, hey, look, that's a huge reduction. You went from 9 bytes to 3 bytes. That's a huge reduction. And yet both of them store the exact same number of 150. And this is where the buffer library shines its glorious powers, because we get to compress data and send that through remote events, but only if you need it. Now, if you wanted to write multiple values inside of a single buffer, this is where you need to keep track of this offset value, which basically represents the cursor of the buffer, because buffers don't have built-in cursors to let you know at what position or what byte you're reading from. You need to keep track of that yourself, manually. So when you write to a buffer, let's actually make a new buffer here. Let's make a 3-byte buffer, and we're going to write 3 8-bit integers to the buffer, 1 for each byte. After each time we write an 8-bit number or integer to our buffer, we need to increase this offset value to whatever the next byte is. So for example, since we wrote an 8-bit unsigned integer here, we need to go to the next byte, so that way we're not overriding the previous value at the same byte. We don't want that to happen. And again, once we write to this byte, we need to set this one to the next byte, which is 2. So here's our 3-byte size buffer. At the first byte, we're going to put 150. At the second byte, we're going to put 200. At the third byte, we're going to put, 250. Let's just do something like that. So now we have a buffer that contains 3 bytes. And then for demonstration purposes, I guess I could send, what should I send here? Maybe a table? I'll send a table with the exact same value. Or actually, you know what? Let's do this as a demonstration of compressing a color3, right? Because if you do color3 from RGB, let's send like white or something, 255, 255. Let's do something like that. And let's say this buffer represents our compressed color3 value, whatever. All right, let's play the game. All right, I'm gonna pause this. Let's take a look at this. Where's my chart? All right, 61 bytes. So here we go. Here is our color3 value. That color3 value is taking 13 bytes. 13 bytes of data for our color3 value, when we could represent it as a buffer, and that only takes 5 bytes. Yeah, look at that. Huge data reduction. 13 bytes to 5 bytes. Let's actually do that. Let's make a function for that. Let's make a function. We'll call this function from color3, and this function is going to return a buffer. And then we need a function to deserialize the data, so we'll call this to color3. This needs to take in a buffer. Assuming this buffer is storing the color3 values, you need to make those assumptions and write your code well. And this returns a color3 value. So this takes in a color3 and gives us a buffer, and then this deserializes it and converts it back into a color3 value. So let's do that. Let's make a new buffer in here, B, and we're going to do buffer.create a 3-byte buffer, 1 byte for each number of the color3 RGB values. And I don't believe they actually get returned as integers. Like if I make a color3 here from RGB and I were to print out like R, yeah, you see how that prints a number? I believe these values are going to be like decimals. So if I do like 4, yeah, it's a decimal. Perfect. So that means because this is a decimal, we can practice converting these decimals into an 8-bit unsigned integer. So we'll just create a constant here. We'll call this 8. We can't really start the name with 8. So we'll just call this int 8. And that's going to be equal to 2 to the power of 8 minus 1. And if we actually print that again, I'll show you. It's the correct size. Oh, oops. I actually need to print the math value. There we go. 255. 0 to 255. This is the upper limit size for an 8-bit integer. Unsigned integer. So basically what we can do with this buffer is we're going to write to the buffer. Let me delete this down here, this stuff down here. And we're going to replace this with from color3. And we're going to do the exact same color3 value here, right there. Boom. Okay, let's write this function. So for the R value, we need to calculate what it's going to be as an integer between 0 and 255. And that's going to be pretty easy because when we access this color's R value, it's going to be a value between 0 and 1. So how do we get the correct int value? Well, let's do buffer.write unsigned 8-bit integer to our buffer at offset 0. And the value is going to be, let's just use math.round. And we're going to do c.r times the upper limit of an 8-bit integer. That way we can see exactly what the value would be as an integer. There we go. We do the same thing for the other colors. So we do green and blue, and we return the buffer. Boom. We have just converted a color3 into a buffer. And then to deserialize the data, we just need to read from the buffer. So to get the R value, the G value, and the B value. So for R, when we get this buffer, we're going to do buffer.read. We're going to be reading an 8-bit unsigned integer, and we are going to pass the buffer, and we're starting at offset 0. So that's our red value. And then we can just kind of do the exact same thing for the G and the B. So we're reading at the next byte, and then here we're reading at the next byte. So there's our RGB values there, and those are integer values, so we can just reconstruct the color3 by returning color3 from RGB. There we go. This function serializes the color3 into a buffer, and this function deserializes the color3 from a buffer. Yeah, let's see how much data we saved. So let's go play the game. Hopefully nothing errors. Perfect, nothing erroring. I'm gonna pause this, look at the packet, open up the chart. There we go. Here is our color3 that's not serialized. It took 13 bytes of data. And then here is our color3 serialized, and it took only 5 bytes of data. That's a huge reduction of data. And now imagine if you have a ton of data throughput in your game, you're passing a ton of data to clients for some reason, or you're passing tons of data to the server, whatever, you can easily reduce how much data you're sending by over half using buffers. But realistically, you should only do this micro optimization if your game actually needs it. Again, you need to go benchmark your game, go to your network statistics, look at the incoming and outgoing data. If this value's consistently below 50 kilobytes per second, then you probably don't need to worry about this kind of micro optimization. Doesn't matter. All right, to represent the true compression powers of the buffer library, let's code a little project here. Let's say we have an ID system and we need to send IDs to clients to tell them to perform some kind of something on whatever has this particular ID. And let's say in your ID system, you know that the amount of these objects that can have these IDs is limited to 16-bit integer, right? So if we do 2 to the power of 16, that's going to be 65,535. Let's say we know there's not going to be more than 65,535 objects at any one point that will have the same ID, so we can restrict the amount of IDs we will have within this range. And let's say every single second or something, 100 of these objects randomly get picked for whatever. I'm just making up a scenario in my head. And we need to tell the clients which of those objects had this thing happen. And we needed to tell them which object that was by giving the ID. Well, guess what? We can either just pass the numbers as is within an array, or we can serialize them inside of a buffer. So to demonstrate this, let's make a for loop, and we're just going to do this 100 times. And let's say we get 100 IDs. So we'll just do, for demonstration, I'm just going to make a random data type. So random.new, let's throw that up here. RNG, random.new, and then we're just going to do RNG, next, integer, anywhere from 0 to the upper range of a 16-bit unsigned integer. That's going to be, we'll call this int 16. That is 2 to the power of 16 minus 1. And for this demonstration purpose, we're just going to generate a random number between there. But we're going to do that for 100 objects. So let's say we have 100 objects with identifiers we need to give to the client. So let's insert into an array. We're going to call this not serialized. And we're going to insert into not serialized the ID of whatever this object is. And then that's what we'll pass here. And then for the second one, we're going to make a buffer for this. So let's do buffer equals buffer.create. And since we know we're going to be passing 100 16-bit integers, each of those takes 2 bytes. So if we're doing 100, 2 times 100, that means we're going to need a buffer with a size of 200 bytes. And then down here, we can do, oops, I want to call this B, not buffer. We could do buffer.write 16-bit unsigned integer into the buffer. And the offset's going to, we got to keep track of the offset. We'll call that offset out here. We start at an offset of 0 or byte 0, and we write this ID in there. So ID. And then once we write, we need to keep track of the current offset position. So we're going to do offset plus equals, and we're not going to do 1, we're going to do 2. And because remember, a 16-bit unsigned integer does not take 1 byte, it takes 2 bytes. So we need to increase the offset by 2. Because the first byte and the second byte are going to be taken up by whatever this 16-bit unsigned integer we just wrote to the buffer is. And then once we do that, we can pass the buffer here as the serialized object. Okay, and now we can go and playtest. Pause this here. Let's take a look at this packet. 1 kilobyte packet. So if we take a look at this table here, I wonder if it's going to tell me the total size. Dang, it doesn't tell me the total size. It should tell me the total size of the buffer though. So here's our buffer. Our buffer was 203 bytes. I guess the 3 bytes are the extra overhead for the remote event. And then here we have our array of IDs, each ID taking 9 bytes, and there's 100 of them in there. So this array took 900 bytes versus this buffer only took 203 bytes. So you can see that's quite a big data reduction or data compression. Now, obviously, working manually with buffers can be quite tedious. So that's where this cool module comes into play. Sera, made by loleris. Let's check it out. So loleris made a post for Sera, which is a low-level serialization library for handling limited-sized dictionaries with primitive types. This library aims to do as few operations as possible to achieve its result while staying a good enough serialization library. Sera's intended purpose is to help with serialization schemas when handling high-efficiency game entity replication to clients. Awesome! So basically how it works is you require the module and you create a schema which basically represents the data that you want to send wherever, either to the server or the client. You can give your keys so you know what each of these things represent, and then you tell it what you want to basically serialize this data into. So for example, the health here is represented by a 16-bit integer. The position is represented by a vector 3 that is also serialized. Reduce the size of the vector 3, and then the name here is represented by a just regular string. And basically what you do is you call this serialize function, you give it the schema, and then you give it the data. And then it serializes it into a buffer, it returns the buffer, you can send this buffer through a remote event, and then on the receiving end, you can access the same schema, so maybe you could create a module and store your schemas in there. You give it the buffer, you deserialize it, and it gives you the original dictionary back to you. And that's it. That's how cool and easy it is to use this module. So let's go take a look at it. So let me go and require the Sera module. And let's say we need to send enemy information to clients about some enemy. Let's say it's going to be the health of the enemy, maybe the shields of the enemy. Maybe the enemy has both health and shields. And the client needs to know what this data is or whatever. This is just a basic example. So let's make a schema for it. We'll call this our enemy schema. And we're going to do Sera.schema. Make a new schema. And we're going to make a table here. And what we want to send to the client, we want to send it the health of this enemy. And what we need to do is access Sera again and tell it what we want to serialize for this particular key value pair. In this case, the health can be serialized let's say health is between, it'll never go beyond the upper values of a 16-bit integer or whatever. So we could say, actually it might, maybe we want to use a float. We'll use a float. We'll use a 32-bit float for the health. And then for the shield, we could do the exact same thing. We could say, hey, Sera, we want a 32-bit float. So we have health, shield, and what else do we want to pass? Maybe this enemy has like a unique ID or something. I don't know. Whatever. Unique ID, and this ID, let's say we know this ID is never going to exceed an 8-bit unsigned integer, right? So we could just do int 8 or uint 8, unsigned 8-bit integer. There we go. So now that we have this schema, let's say we have our serialized enemy info here. We're going to use Sera, and we're going to serialize using this schema, enemy schema. We give it the table of data, so the health, let's say the health of this enemy is 250.75, and let's say the shield of the enemy is 75.150 or 155, something like that. And then let's say their unique ID is, let's just say it's 255. So here's our enemy information we want to give to the client. We serialize it into the, using the enemy schema. It's going to return to us a buffer question mark because this might error. So basically what we're going to get is serialized enemy info and a possible error message. So if we did not get the serialized enemy info, then we can just print out, or you could warn what this error message is. Otherwise, we're just going to assume that it's serialized correctly because I don't see anything wrong with this. Our thing matches the schema just fine. So we're going to pass our serialized enemy info. And actually, let's make this enemy info an actual table here. That way we can also pass it to the remote event. So enemy info, boom, boom. Actually, this should be swapped. So serialized enemy info goes here, enemy info goes there. Boom, bada bing, bada boom. And then on the client side, let's say we had access to the schema as well. Maybe the schema is stored in a module script somewhere. Let's make a module script real quick. Module, we could call this enemy network or something, I don't know. And then we could store our schema in here. So actually we could go and we could do this real quick. We do dot enemy schema is equal to this. Let's pull in the Sera module in here. There we go. And that way in the local script, what we're going to do, be able to do, because the client's going to have a buffer and that's not very useful for us. So we actually need to get our enemy network to access that schema as well as Sera. So let's get Sera in here too. And then what we can do is we can get the enemy information here by doing Sera.deserialize. Let's pull in our enemy network, get the enemy schema, and then we need to pass the buffer here. That's going to be what value is. Actually, no, value is going to be this. Go back to my script. Value is going to be this table. So we actually need to access the serialized key, so that way you can actually see it being deserialized. So we're going to do value.serialize. Okay, let's try this out. Hopefully nothing errors. And then for giggles, let's print this enemy info out into the console. Okay, we got an error. Attempt an XNL with numeric. Why do we have error? Oh, oops, I forgot to replace this here. My bad. Let's pull on the enemy network. Let's get enemy network, enemy schema. There we go. All right, let's try this again. Missing field unique ID. What? How am I missing field unique ID? I thought I put that in there. Did I not put that in there? Oh, I didn't. I'm a goofball. This is why the serialize function might error, because you might be a goofball and mess things up. Okay, now it should work. There we go. Perfect. It's working. All right, let's take a look at our packet here. Pull this out. 109 bytes. So as you can see with the not serialized table, obviously when we sent that information over to the client, we had to store, not only did we have to store the values, but we also had to store the key value pairs here. So we had to send over the string for shield, the string for unique ID, as well as the string for health. Each of those took up a lot of data because each character in a string is a single byte. So this is a 10 character string that took 10 bytes. And then each number in here took 9 bytes because all of these are 64-bit. So in total, let's print out what the total is. We got 8 plus 10 plus 8 plus 9 plus 9 plus 9. Print that out. That took 53 bytes to send this dictionary over. But by using Sera and using the buffer, we only got to send over 11 bytes of data. That's a huge reduction, 53 to 11 bytes. And yet, on the client side, because we have access to that schema, we were able to deserialize this buffer back into this dictionary, and it stores the exact same values. Look at that. How epic is that? So my friends, those are basically buffers in a nutshell. If you want to use them probably want to use the Sera library. It's the most straightforward and easy to use library for compressing data and sending it through remote events. That's the primary usage for buffers, but you can also use them in data stores and memory stores to serialize data and then store that inside of your data stores and then deserialize it on the receiving end. You could do that too, but realistically, you'll probably never ever hit data limits for your data stores. Even Roblox themselves said like only 100 games out of like millions of them ever got beyond like certain limits they've set. And that's probably because of just bad coding practices, but you'll probably never hit the limits for data stores. It's not something you want to worry about. So buffers are only really for certain optimizations. The likelihood you'll use the buffer library is quite low. So unless you have a lot of data throughput in your game's networking, you probably won't benefit from optimizing with buffers. If you don't need to store a lot of data, because you'll probably never hit the limits, you won't need to use buffers. But where buffers really shine, like we showed, is when you need to work with a lot of binary data for things like your own custom replication and data compression, but it could also be useful for other things. Like if we go to the dev forum post, they mentioned in here why are buffers useful. They could also be useful for terrain serialization, audio and imaging processing if you need to do that, as well as what we just did, which was custom replication and compression, hashing, as well as implementations of other virtual machines that can benefit from a buffer type. So the use cases are kind of limited, but when you are able to use it and you benefit from using it, then use them because they are very useful. It's definitely a fun library to mess around with, and I encourage you to mess around with it and try it out nonetheless. I mean, it's always good practice to, mess around with your programming skills and learn new things like the buffer library. So thank you for watching. Hope you enjoyed this video, and I will see you in the next one.